say pure rolling means the body is rolling without any slippage. If this body is rolling over this surface, then the point of contact, that is this point which is equally shared between this rolling body and this surface, that is stationary. There is no slippage between these two surfaces. And this is also called the instantaneous acceleration, because at this moment the whole body has a tendency to just have a rotation about this axis, about this point. It is the whole body is rotating. As it slightly rotates, this point which is in contact with this body, this also slightly shifts. But at this instant, the whole body is revolving with the angular velocity omega about this axis. Whether you say about this axis or about this axis, that's one and the same thing. Angular velocity is characteristic of the whole body. So we say that is point P is instantaneous axis of rotation. It is only when this is pure rolling. That is, there is no slippage between these two surfaces. Then P is instantaneous acceleration, and at this instance the body is revolving about this axis. Theta, omega and alpha, they will be characteristic of this rotating body. They are going to have same value for the whole body, whereas the linear parameters like S, V and A can be different depending upon what is their distance from the axis of rotation. Now over here, if this body is revolving with angular velocity omega, and if you have to find what is the velocity of this point, so obviously we can use the formula V is equal to R omega. So for that, what we do is, if we take this point P, we join these two. This is revolving with angular velocity omega. We join these two and the velocity will be perpendicular to this, and this will be revolving in this circle, keeping this as a radius. Similarly, the other particle, if you have to see, that is in which direction it will be moving. So what we do is, we join these two lines and the velocity will be perpendicular to this, and this will be moving in this circle of this radius, So we can use V is equal to R omega, where V is the velocity of the particle which is situated at a distance R from the axis of rotation, and omega is same for the whole body. Similarly, over here, if this is instantaneous acceleration and we are interested, let's say, in finding the kinetic energy of this body, whole kinetic energy of this body, so what we can do is, so let's take 2 or 3 points to find the total kinetic energy of this body. So if we take this particle of mass m1, this is instantaneous acceleration, so we join these two, and let's say this is distance is r1, and this will be moving with the velocity v1 at this instant at an angle of 90 degree with this r1. So this particle shall be moving in a circle with this as center and this r1 as a radius of this circle, and angular velocity will be omega. Similarly, if we are interested in finding this v2, so what we do is, we join these two. So this is going to be r2. Let's consider the particle of mass m2 over here. The velocity is going to be at an angle of 90 degree. This is m2, r2, let's call it as v2. Similarly, let's take particle m3 over here. We connect this and let's say this is called r3. So this particle shall be moving in a circle of radius r3 in this direction at an angle of 90 degree. Omega will remain same, so this is going to 90 degree, and let's call it as v3. So omega is going to be same for the whole body. So omega is same for m1, m2 and m3 about this point P, it is going to be same. Now if we have to find the total kinetic energy of this body, so total kinetic energy of this body which is in pure rolling motion, it is equal to kinetic energy of this plus kinetic energy of this plus kinetic energy of this plus kinetic energy of all the particles individually. If we add these kinetic energies of the individual particles, that will give us the total kinetic energy of this body which is in pure rolling motion. So total kinetic energy of this body, we can say that is kinetic energy of particle 1 plus kinetic energy of particle 2 plus kinetic energy of particle 3 and so on. Kinetic energy is a scalar quantity, so we can algebraically add or subtract. That's why the total kinetic energy becomes equal to, that is for m1 if we say, so it is half m1 v1 square. For second one, half m2 v2 square plus half m3 v3 square and so on. So it is half m1. Now v is equal to r omega. If so, v1 is going to be equal to R1 omega, V2 is going to be R2 into omega, V3 is going to be equal to R3 into omega, that is omega is going to be same for the whole body. So V1 is going to be equal to R1 omega square plus half M2 R2 omega square plus half M3 R3 omega its whole square and so on. So this comes out to be half M1 R1 square omega square, half M2 R2 square omega square, half M3 R3 square omega square and so on. So half omega square we can take it out. So this comes out to be M1 R1 square plus M2 R2 square plus M3 R3 square and so on. What is this whole thing? This stands for the basic definition of moment of inertia of this body about this axis. If this is made of very small particles, so moment of inertia about this axis of the whole body is summation of moment of inertia of M1 about this axis plus M2 about this axis plus M3 about this axis, and moment of inertia of particle about this axis is obviously M1 R1 square plus M2 R2 square plus M3 R3 square and so on. So this can be written as, this is going to be half omega square, we can call it as IP, that is moment of inertia of this whole body about this axis. But we know that is this point is the center of mass. So we can use parallax theorem, that is we can say IP about this is equal to ICM plus, if the radius of body is R, plus it can be written as mr square, because parallax theorem what it says is that is moment of inertia about this axis is equal to moment of inertia of this about the line passing through center of mass plus m into this distance square. This distance is R only. So IP is equal to ICM plus mr square. So let's put it over here. So this comes out to be half omega square, IP comes out to be ICM plus mr square. Let's open it. So it comes out to be half ICM omega square plus half omega is what? This we can say is at this moment, suppose this is moving with VCM. So omega is also VCM upon R. We can write it like this. At this instant, suppose center of mass is moving with velocity center of mass. Half ICM omega square plus half omega square, let's write it as this square. So it comes out to be half ICM omega square plus half omega, let's replace by VCM by R, VCM square by R square into mr square, which comes out to be is equal to half ICM omega square plus half MVCM square. Very, very important result. So it means if we have to find the kinetic energy of this body which is in pure rolling, so either you can do it, that is you can find the total kinetic energy of this body taking this as axis and the whole body is revolving about this axis, and this is also equal to pure rotational energy about the center of mass, half ICM omega square, plus the translational energy as it has been a point mass, that is the translational kinetic energy, that is half MVCM square. So the total kinetic energy, either you say that is a pure rolling about this axis, the whole body is revolving about this axis, and that is also equal to the rotational kinetic energy about the center of mass plus half MVCM square, that is the pure translational kinetic energy of the center of mass.